Hey everybody, we are continuing on where we left off. So remember what we did last time was we derived the first state, the ground state. So right here we're showing the first excited state. So let me get to the previous slide. There we go. And we found the normalized ground state here of the quantum harmonic oscillator. And we can see here that it's this nice sort of Gaussian function, and that its energy level is h bar omega over 2. And then the next thing we did was we used an equation that allows us to get the next state, the excited state. And if we look down here, you can see that what we did was we used this equation here, right? So we use this equation, and with n equal 1, because we were after the first excited state. So we were after this state. So some normalization constant we don't know, a plus to the n, where n is 1. So just one application of a plus on psi naught will give us our psi 1 of x. So on this previous, on the slide that I showed you when we came into the meeting, or into this video, shows that we did all that. So what we said is like, okay, psi 1 is a plus psi 0. And I left the a off here, but I really should have kept it through everywhere. So I should probably put it back, just stick it back here. So the a1 just sort of hangs out. a1, a1. And see here, I put it back. Okay, and we got this function, and literally all we did was use the fact that a plus is really a differential operator, right? It's minus h ddx after you put in, substitute for what the p-hat operator is, plus m omega x times some constants. So it operates on psi naught, which is here, right? So you take derivatives, you do some algebra, and you end up with this, and then you have to normalize, and it turns out really cool that a1 is just 1. That's really cool. Notice that a1, the normalization constant for the first excited state, psi 1, was 1, but the normalization constant from the previous slide for the ground state here was definitely not 1. So notice here we had a normalization constant here, normalization constant here that we were having to solve for at some, right? And we found it was this, definitely not 1. So the question now is, if we want to have more excited states, like not just n equal 1, but n equal 2, n equal 3, as many as we want, we would like some kind of way of getting at those states and not having to normalize every single time. Okay, now I told you before that, getting those states by using these operators is pretty tedious, and people have done that, and they have also solved the differential equation, the original differential equation, the TISE, with the harmonic oscillator potential energy function. They've solved that in different ways as well, and so you're not going to have to apply a plus, n times to get your psi 5 or whatever you're after. But it is very useful to know what the normalization constants are, because it turns out, and I'm going to be showing you that pretty soon, that we have, they're known functions, these, the psi's. They're proportional to known functions called the Hermite polynomials, which we're going to get to. And so if you know those, but you still don't know the normalization constants, it's kind of a pain to have to normalize every single time. So that's what we're going to work on next, is just get these normalization constants and be able to use them. All right. So here's where we were, where we got our first excited state. All right, so I'm going to get a new layer, and I'm going to label it as we always do. Excuse the interruption. What is the date tomorrow? Is 13, 2021, and this is our first slide of the evening. All right. Okay, I'm recording this at night. All right. Okay, so we would like to, let's turn off this one. We would like to be able to normalize these things, or have a normalization constant that we already know, and not have to do integrals every single time when we look up at the functions. Okay, so let's just write down what we know. So we know this. We know that we have if we apply a plus to some psi n, that we get, psi n plus 1, right? We get the next level up, as we know, and some normalization constant. I'm going to call that C here. Now, I was calling it A before, but I'm going to call it C. And that there's probably a dependence on n. We saw that already. The normalization constant for A0 was a bunch of, pi's and all kinds of stuff. And the normalization constant for psi 1 was just 1. So there's some dependence on n, right? It's going to change with n. So we know that. We also know that if you apply a minus to, get that way, okay, to psi n, that we get some, we know so that's going to lower it down 1, and that there's going to be some constant. And that these two things, the CNs and the DNs, are unknown. Okay, so we would like to find these two things. All right, so how can we do this? So we're going to have to use a couple of things. It's a little complicated how to do this, all right? We're going to use our knowledge of the raising and lowering operators, etc. And to set this up, I'm going to need to work out a particular thing. So what I'm going to do is I'm going to work out this. I'm going to use this result, and this result is f star. So let's say we have some function. So we have functions f and g. Oops, and g. Now these functions I could have used just psi 1 and psi 2 or something. But I didn't want you to get confused, like they're not specific psi's. They're just some functions that are in, that are like psi, okay, or like any of the psi's from any of the systems we've studied. Okay, anyway, they're square integrable. That's all you really need to know. So a plus a minus acting on g dx. We want to prove, or we want to use this fact, and I'm going to prove it first, but I want to use the fact that I can write this as a minus plus acting on f all star g dx. And this property, where notice here we have the a plus minus acting on g, and over here we have the a minus plus acting on f, and everything's starred. This is actually has a name. This is called hermiticity. And it has a big role in quantum mechanics that we're not really going to hear about again until we get to chapter 3. So, and that's probably not going to be in this class. It'll be in the next class. But just to point out that this is sort of foreshadowing of what we're going to be doing in chapter 3. All right, so first we really need to prove this. Can't just state it. All right, so let's do it. It's not too bad, but we do have to do some work. Okay, so again, we know a plus minus, right, is 1 over the square root of 2m h bar omega. And then we have its, I've got to look at my, yeah, here we go. It's minus plus I p hat, right, plus m omega x hat. Okay, all right, so we know that. Now I'm going to write this, we've written this before in a different form. I'm going to substitute in p. Remember p hat, I'll stick that over here. P hat is h bar over I d dx, right? So I'm going to use that here. So I have 1 over the square root of 2m omega h bar. Let me make sure that's the right constant because I always forgot that. Okay, yep. And then we're substituting for p hat. So this is the i's will cancel out. And I just get minus plus h bar d dx plus m omega x. Okay, so now we've got our operators a plus a minus. Okay, so now we're going to substitute them in here. And I'm actually going to substitute them in here into this one here, but I'm going to do it in pieces. Okay, so let's just look at this integral. Let me get a different color because I'm going to think about just looking at this one. Okay, so down here in blue, we're just going to look at this one. So I'm going to write it again, minus infinity to infinity, F star, and then A plus minus acting on G dx. And now I'm going to put in all the pieces here, right, for A star. So first, I'm going to bring out this constants out of the integral because I can. So I'm going to put 1 over the square root of 2m omega h bar, and then I'm going to put my parentheses, and then I'm going to put an integral, my integral. I'm going to drop the minus infinity to infinity. It's there. I just don't want to keep writing it. So this is an integral sign here. And then I have the F star, but then I have the A plus acting on G. So the A plus here, or sorry, A plus minus is minus plus H bar D dx, and then plus M omega x, and that's acting on G, and then everything's being integrated by dx. I'm going to split this into two integrals. Okay, so I have 1 over the square root of 2m omega h bar. Then I have, oops, that's supposed to be a big like that. Okay, so here we go again. We have two integrals. One is minus plus h bar outside of the integral of f star times dg dx. Okay, and then the other integral is plus m omega outside the integral of f star x g dx. Okay, great. Now we have two integrals to deal with. And here's where I'm going to sort of take them off by themselves. Okay, so I'm going to grab another color, and let's see, we're going to go to, I have to do something like that. Okay, I'm going to look at this one here first. Okay. Now I'm just going to grab just this much of it. Okay, so in pink, we have the integral f star dg dx dx. Now remember what our goal is here. Notice that I have the A applying itself to G, right? So this is the operator. It's going to act on G, the function G. Again, think of it like a psi, okay? It's just a member. Think of it as a solution to the TISE, right? It's just some function that's a solution to the TISE. It doesn't have to be, but it's good to think of it that way. All right, now it's acting on G, but what I'd like it to do is I want it to act on F instead, right? That's what I want. So I want this, for just this one little piece, I would like this derivative to act on the F star instead of the G. Well, there's a great way to do that, remember? It's integration by parts. Now, I'm not going to go through that derivation again. Back weeks ago, we did it in class. It is a common technique. In use in quantum mechanics and pretty much everywhere, but so if you don't remember that, please go back and remember what we said, right? If we have functions like f and g, which are like solutions to the TISE and are square integrable, they have to go to a 0 at minus infinity and infinity. So when I want to do integration by parts, all it means is that I'm going to take a derivative off of one thing in the integral, take the derivative off the thing it has, the thing that is being taken the derivative of. So in other words, I'm going to take the ddx off of g, and I'm going to put it on everything else that's in the integral, right? And everything else happens to be just f star, okay? And I just pick up a minus sign for my trouble. That's all integration by parts is going to do for me, okay? So I get a minus, and then I get an integral. And again, I'm going to leave the minus infinity off and just put it on there for to remind you of what the integral looks like. And then I'm going to put df dx, and it's f star, right? G dx. Okay, well, I can write that again one more time as minus the integral df dx and star, right? Okay, times g dx. All right. Now let's remind ourselves that we have this plus or minus h bar in there. So I'm going to stick that back in here now. So it's coming back. So, and I'm going to put a little arrow here to remind you that this is just coming back. So we have the minus plus h bar. We have a minus sign here. That'll make it plus minus h bar. So plus minus h bar, the integral df dx star g dx. Okay. And now I just want to remind you that a minus, right? So if I were going to write this one more time over here, I'm going to write it one more time. I'm going to get in my yellow color again. I'm going to write it here. I'm going to put the minus on the top this time, just writing it differently. So minus plus is equal to the same little, constant 1 over 2 m omega h bar. And then this would be plus minus. So plus is the top sign, minus is the bottom sign. H bar d dx plus m omega x. Okay, so notice here, right, we have plus minus h ddx, right? Plus minus h ddx. So this seems to be part of, a minus plus. Notice that's what we want here, right? Okay, so we have that part, good, we're good. Let's do this other part. Get another color, I'm gonna get a red color, and we're gonna do this one. And I'm gonna take my constants with me this time because it's an easier interval. So I'm gonna have m omega, the integral f star, so I'm just writing it again, x g dx. Now notice that x is just x is always real, okay? It's not a complex number, it's just x, right? Just position of the particle, representation of position, okay? So it is real, so I can pull it in under the star and nothing will change. So this is going to be m omega, the integral x f, or x or fx, either way, doesn't matter. Oops, sorry, let me fix that. Okay, and this there, and then star, and then g dx. Okay, so notice here, this was xg, and now this is going to be x f star. So notice here, so we have the integral, and I'm bringing the constants back in, m omega x f all star g dx. Okay, so now we notice that is the other part of a minus plus. Because remember, a minus plus, like this sign never changed. The plus sign on the x part never changes. So we're good, right? We have a plus sign here. Okay. So now I put it all together and I can see, go back to my blue color, I can see now that the integral of f star, going back up here, a plus minus g dx is, in fact, equal to the integral. So I'm just pulling everything together now, okay? We just showed we had, this is part of a minus plus, this is part of a minus plus, stick it all together with the constants, and you're going to get the integral of a minus plus, right, f star g dx minus infinity to infinity on both integrals. Okay, I'm sticking everything back. So QED, which means we've proven this is to be true. Okay? All right, so we're going to use that when we're doing the work we need to prove, to figure out what CN and DN are. All right. Okay, so we're going to use this fact, and I'm going to start a new layer because I need some room. Okay. All right, so again, pause the video if you have not caught up. Okay, so let's get a new layer. And again, I'm going to name it real quick. 413, 1, 2. Okay, all right, and new layer. Okay. Okay, so now let's write down a quantity that looks like this. Start here, minus infinity, the integral minus infinity to infinity. And we're going to write down a plus minus acting on psi n star times a plus minus acting on psi n dx. Now remember, we have a plus acting on psi n is, let's see, what did I use? Sorry about that. Let me go back. Just remember the thing. So Cn psi n plus 1, and A minus acting on psi n is Dn psi n minus 1. Okay, n, not m, n. Okay, just writing that down again. Okay, so notice now in the previous slide, right? So I'm going to turn this off again and go back. In the previous slide, no, I want you to note whenever we have an A plus, whenever we have an A plus or an A minus acting on a G, we can bring it over and act it on here as long as we change it. So if I had an A plus acting on G, I can bring it over to this side and change it to an A minus acting on F, and then star on everything, right? Or if I had an A minus acting on G, I could bring it over to this side, right? And just change it to an A plus acting on F, all star, okay? This is gonna help us. So that's what we're gonna use. We can move these things around as long as we're changing the minus to a plus on the A plus minus. Okay, so let's go back to here. All right, so I'm going to actually bring this guy over here and apply him to this to this quantity here. So I can move him, remember? So all I have to do is change that sign around. Okay, so this is going to be the integral. Again, I'm going to drop off these minus infinities to infinities because they're just a pain in the butt to carry around. And I'm going to have A minus plus, because I changed this to minus plus, and then I have an A plus minus, which was already there, this guy here, and then psi n star psi n. Okay, dx. Okay, great. But what is this thing? Okay, well let's write it down. So actually, I'm gonna put that in orange color here, and we're just gonna look at that by itself here. Okay, so we're gonna go A minus plus A minus A plus, sorry, plus minus psi n. Let's figure out what that is. We can do that because we do know something about this quantity A minus plus, right? We remember that we've had the Hamiltonian in terms of this quantity, right? So if we think about it, all right. So let me go back and write down the Hamiltonian. So we have the Hamiltonian operator, right, in terms of our A plus minus, is h bar omega times A minus A plus minus 1/2, right? Or we can also write it as h bar omega A plus A minus plus 1/2. Okay, there's two forms, whether you're doing the A plus A minus or the A minus A plus. Remember, they don't commute, right? Okay, that's, you can easily derive, you start with one of these and derive the fact that you get a positive because these don't commute, and the commutator of A plus A minus is 1. Okay. All right, so we're gonna come back here so we can see that A minus plus, so we can rewrite all this like in this notation where we're keeping both of them like that. So we can say the Hamiltonian is h bar omega A minus plus A plus minus, and then the top sign is going to be the minus and the bottom sign will be the plus 1/2. This is just a compact way of writing this, these two things. Okay, so if we notice, if we want to solve for A plus minus, right, we can in terms of the Hamiltonian. Why is that helpful? Because we know this. We know the Hamiltonian acting on psi n gives us En psi n, right? And remember the En, why are there too many things on E? En is equal to h bar omega n plus 1/2, right? So we know that. This is omega, not m. H bar omega n plus 1/2. Okay, so we know this. So if we can write things in terms of the Hamiltonian, we're going to have a better time, right? We can know what this is. All right, so let me solve. So we have A minus plus A plus minus is going to be, let's see, equal to the Hamiltonian over h bar omega, and then plus minus 1/2, right? So we divided by h bar omega, then we move the 1/2 to the other side, and we got the plus minus. Okay, all right. So let's do this separately, right? So I'm going to write this out. This is actually two things, right? This is a minus a plus acting on psi n, and or, right, pick the bottom sign, a plus a minus acting on psi n. So it's actually two things. And as we see, we have both of these here. So I can use either one of them that I want. Okay, so let's look at a minus a plus acting on psi n. What does that do for us? Okay, so a minus a plus, that'll be the top sign. This will be h hat, the Hamiltonian, over h bar omega, and that'll be the top sign, right? So that's plus 1/2. Why do I have minus 1/2 here? Okay. Oh, yep, I messed up here. Sorry about that. No, I don't think I did. Let me figure that out. I'll be right back. Got a minus sign problem. Maybe you guys pause the video yourself and see if you can find it before I get back. Well, it's gonna be pretty quick. All right. Okay, actually, no minus sign error. Yeah, I don't think so. All right. So let's. So we know this is true. So I'm gonna act this on psi n, right? And what do we get? So we get h hat over h bar omega acting on psi n. I know what to do with that. And then, whoops, not equals, plus. And then this one's just 1/2 times psi n, plus 1/2 times psi n. This guy here is En psi n. So we have En over h bar omega, and then psi n, and then plus 1/2 psi n. And writing it out here again, En is this stuff over here, so the h bar omega will cancel with this one, and we get n plus 1/2 psi n plus 1/2 psi n, and therefore this is just n plus 1 psi n, combining this 1/2 and this 1/2 here. Okay, so n plus 1 psi n. So that's what this a minus a plus psi n gives us. Okay, let's write that up here. A minus a plus psi n is equal to n plus 1 psi n. So notice that even though a plus definitely is raising my psi to n plus 1, the a minus comes back and lowers it again to psi n. So I should expect it to be proportional to psi n, not psi n plus 1, right? Because I have two of them. So when you raise, you're going to raise this one, raise it with a plus, but lower it back down with a minus. Okay. All right. Let's do similarly, right? We're going to have the a plus, a minus. So a plus, a minus, that's the lower sign here, acting on psi n. And over here we have, again, we're going to take the bottom signs now. We have the Hamiltonian over h bar omega, and then we have minus 1/2 acting on psi n. And again, we're going to have the Hamiltonian acting on psi n over h bar omega minus 1/2 times psi n. And this is going to be the Hamiltonian acting on psi n is En psi n over h bar omega minus 1/2 psi n. And that's going to be h bar omega. Oh, sorry. We don't need those. They cancel, right? Because when I put En in, it's got an h bar omega, and I got one down here. Okay, so they're going to cancel, so we don't care about those too much. We're going to have n plus 1/2 times psi n, and then we're going to have minus 1/2 psi n. The 1/2s will cancel here, and I'll just be left with n psi n. Okay, so now I know that a plus a minus psi n is just n psi n. Okay, now notice again, same thing. This lowers my state psi n to psi n minus 1, but then a plus raises it back up to psi n, which is why we have a psi n over here. Okay, well, we have this factor of n sitting out front. Okay, great. So now let's take, let's go back to our original thing, which is here, right? This integral here. This is our original integral that we were messing around with, and we wrote it like this, and we figured out what all this is, okay? So I'm going to come down here in blue again, and I'm going to write it out. So I'm writing it again. I'm writing this exact thing right here again. So the integral minus infinity to infinity of a plus minus acting on psi n star times a plus minus psi n dx. Okay. Now if we notice, look over here, a plus acting on, and actually, I'm actually going to pick a sign first, okay? So notice here I have plus minus and plus minus. I'm just gonna pick sign. I'm gonna let this to be the one for plus. So I'm just gonna even erase that bottom sign and just not even, right? I'm just gonna pick a sign here and do just that integral with that one sign. So both of these are a plus. So notice up here, a plus acting on psi n, I can replace with cn psi n plus 1. I'm gonna do that in both of these places, okay? So here we go. So integral, I'm going to leave off the minus infinity to infinity because it drives me nuts. And then I'm going to replace this with cn psi n plus 1 star. And again here, cn psi n plus 1 dx. This is going to be cn star. This is going to be cn. They're both constants. They can come out of the integral. And I get this is equal to cn squared. That's short for cn star cn. Integral psi n plus 1 star psi n plus 1 dx. Okay. Now, so I have this side, but notice that when I pick a sign here, I can also use this, right? So this was this integral here. This guy here is this integral here, right? But I can use this side when I can also use this side, right? So here, so I'm gonna write that here. So equals, now I picked the top sign. So this is the integral of a minus, right? A plus, picking the top signs, right? Psi n star psi n dx. Now I know what this is, right? A minus a plus psi n. Look here, a minus a plus psi n is n plus 1 psi n. Okay, so now I can write that here as n plus 1 can come out of the integral because nobody cares about that being out of the integral, right? It doesn't have any dependence on x, it's just a constant. And we're left with psi n again, psi n star psi n dx. Okay. So now, if you look, right, even though this is, even though this here is psi n, and this is psi n plus 1, right, we have an equivalence between these two things. So we have this guy here must be equal to this here, right? Okay, so this tells me that Cn is equal to n plus 1, well, sorry, square root of n plus 1. Okay, right, so if I say these two have got to be the same. Okay, so, all right, so if we say that, then we can do a similar thing with the other sign, so a minus, right? All right, so let's do that. So we have, let's go in green color. So we have the integral, now we're going to take the bottom sign, so the integral a minus psi n star a minus psi n dx, that's going to be equal to the integral of, remember the dn's, right? So we're going to substitute dn psi n minus 1 star dn psi n minus 1, minus 1 dx. Okay, again, that's going to give me dn squared and the integral psi n minus 1 star psi n plus 1 dx. Okay, and then we can use the other side again, just so we did last time here. And we have, this is going to be the integral of a plus, we're using the bottom sign, a minus psi n, right, all star psi n dx. And remember we said a plus a minus is just n psi n, so we have, I'm bringing the n out of the integral psi n star psi n dx, and therefore dn is equal to the square root of n. We're making these two things equivalent. Okay? All right, so now we can replace these things up here, right? So I'm going to do that down here, and we'll do that in our red color. So finally, we have the equation a plus acting on psi n is equal to Cn, which is the square root of n plus 1 psi n plus 1. And then we have a minus acting on psi n, gives you the square root of n psi n minus 1. Okay, so that's great. This now tells us the normalization constants when we move up and down a level. Okay, now it's often convenient to write your state, like your psi 5 or whatever, right, in terms of the ground state psi 0 and not in terms of psi 5, or sorry, psi 4. So in other words, if I said here, oh, well, a plus acting on psi 4 will give me this, right? It'll give me square root of 5 psi 5, great. But it would be also good to know what can I do to get psi 5 just from psi naught, psi 0. Okay, that's what we're going to do in the next layer. So we're going to go plus this, and we're going to name it. All right, and let's get our yellow color again. All right, so let's notice from our previous equation that psi 1, and actually let's write them down again. I'll write them in my red color again. So I'm going to write them here. We have a plus acting on psi n is the square root of n plus 1 psi n plus 1. And we have a minus acting on psi n is the square root of n psi n minus 1. Okay. So as an example, let's just do a couple of examples because sometimes these can get confusing. So the example I just get was psi 5. So for example, okay, so let's say, so a plus acting on psi 4 will give me psi 5. So n plus 1 is 5. So you put 5 here, square root of 5, psi 5. And a minus acting on psi 5, right, will be psi 4, n minus 1 is 4, but this is 5, so this will be also square root of 5 psi n, sorry, 4, right? So that's how this works. So you do a few of them to convince yourself you can get the right thing under the square roots. All right, so let's go back to the color. So I'm just kind of turning things around now. So let's look. We had psi 1 over here, right? So this, if this was 1, n would be 0. So if n is 0, we get psi 1 here. We get 1, square root of 1, and we get a plus psi 0, okay? So that's what I'm doing here. So psi 1 is equal to a plus psi naught. Yeah? And psi 2 is equal to, let's see. So we have this, if n was 1, this would be psi 2. This would be the square root of 2. This would be psi 1, right? Okay, so this would be 1 over the square root of 2, psi 1. Oh, sorry, a plus psi 1. Sorry, a plus psi 1. So now keep going. So psi 3 is going to be, let's see here, right? So let's say so it's psi 3 when n is 2. So this is going to be psi 3, n is 2. This is going to be the square root of 3, and this is going to be psi 2. Okay, so it's 1 over the square root of 3 psi. A plus psi 2. All right, so we've got a few examples here. I could keep going, but I'm not going to do that because what I want to do now is I want to now keep going with this in the sense that I'm going to now write this one in terms of psi 0 because I know what psi 1 is. Okay, so let's write psi 2 again. Psi 2 is equal to 1 over the square root of 2, a plus psi 1, right? So we have a plus, but psi 1 is this. So I have a plus psi 0, right? And let's write psi 3 for the heck of it. Psi 3 is 1 over the square root of 3, a plus psi 2, which is this. So 1 over the square root of 3, 1 over the square root of 2, a plus acting on a plus psi 0. Okay? And just for the heck of it, psi 4, which we didn't write, but you can prove this to yourself, is 1 over the square root of 4, 1 over the square root of 3, 1 over the square root of 2, a plus to the 4th acting on psi naught, right? Notice this is a plus to the 3. Okay, so now we can think about a general formula. Notice this is the square root of 4, square root of 3, square root of 2. And psi 5 would be the square root of 5, square root of 4, square root of 3, square root of 2, a plus to the 5th psi 0. Okay, so we can write down a general formula just by looking at this, where psi n is equal to 1 over the square root of n factorial, because notice 4 factorial is 4 times 3 times 2 times 1, and 1 over the square root of 1 is just 1. So this works. A plus to the n acting on psi naught. Okay, so that's cool. That will be helpful. Now remember that whenever we're solving for solutions, whenever we get solutions to the time-independent Schrodinger equation, they're always what we call orthogonal, right? So if you integrate two of them that are different versus each other, right? So if you integrate two functions, let's say psi 1 and psi 2, because the 1 is different from the 2, right? The ends are different. You'll get 0. If you integrate psi 1 star psi 1, you should get 1, right? If they're normalized, right? But you're 0 if you're integrating psi 1 star psi 2, or psi 1 star psi 3, or psi 2 star psi 5, or whatever, right? So that the way that we write that down again, remember orthogonality, and we'll get the orange color. So orthogonality is this idea where you have the integral from minus infinity to infinity psi m star psi n dx is equal to delta mn. Remember, we had that Kronecker delta. That just says it's 0 over the integral is when m is not equal to n, and 1 when m is equal to n, right? Okay, so the orthogonality, but we'd like to prove it for this case. I think we'll leave that because that's going to take a while. But if you look in your book, they do a proof of this, and you can easily work through it. All right, now the next thing we're going to be doing is a worksheet. And the first part of the worksheet is literally redoing how we found psi 1 by applying A plus to psi 0. And I did that for you in the previous video, so that's a freebie, but I would try to do it yourself, okay? And the second part of the worksheet, you need to think about what, and I believe this was I think it was part of one of your tests, or quizzes, I believe, where we wanted the P operator and the X operator written in terms of A plus minus. And the reason that we do that is to make calculations of expectation values work. Okay, so I'm going to give you the answer for that particular problem, so to get full credit for your quiz, if you haven't already done it, right? You can see this video tomorrow, and I think the quiz is due Thursday night. You need to show all your work. Okay, so for this, we're going to need, your worksheet that you're going to have needs the fact that we can write x hat, the operator, as the square root of h over 2m omega, a plus minus a minus. Oh no, plus a minus, sorry. And we can write p hat as I times the square root of h bar m omega over 2 a plus minus a minus, okay? All right, now, why is that useful? Let me show you an example. You're going to be doing something like this in the worksheet. And I'm going to give you an example. Give me a second. Okay, yep, I'm going to give you an example. And then I'm going to let you go, and you're going to work on the worksheet for your homework. Okay, so I'm going to give you an example. I'm going to look at calculating the expectation value of p hat. Okay, expectation value of momentum. Okay, so usually, right, as you know, it's to get an expectation value, you take psi star, put p acting on psi, right, x on psi, dx, right? Let's make the whole sandwich. P acts this direction, right? But here we're going to ask you, what is the expectation value with respect to a state in the quantum harmonic oscillator of a state n? So in other words, psi star n, right? P psi n dx, okay? And now P, I'm going to write it in terms of these. Okay, all right. So I'm not going to write, h bar over I ddx and then try to take some derivatives. And how could I do that anyway? I don't even really know what psi n's are. I know what psi 0 is and psi 1, but I don't know some general psi n, right? Okay, so I'm going to do that. So I'm going to pull my constants out. So I have I square root of h bar omega m over 2. And then I have the integral psi n star, and then I have a plus minus a minus psi n dx. All right, this is going to be two integrals. I'm just going to look at this. No, in my green color. I'm just going to look at this guy here. It's two integrals. So we have the integral psi n star, a plus psi n dx, and then minus the integral psi n star a minus psi n dx. Okay, well, we know what a plus and a minus do now, right, from here, right? So a plus on psi n, I know exactly what to put there. So I'm going to do that. So I get equals the integral psi n star, that doesn't change, A plus psi n gives me square root of n plus 1 psi n plus 1. So I'm going to bring the square root of n plus 1 out because it doesn't need to be in the integral. And psi n plus 1 dx. And over here, a minus on psi n does this, square root of n psi n plus 1, n minus 1 I mean. So I'll bring the square root of n out, integral psi n star, and then psi n minus 1 dx. Now I want you to notice, right? Remember the orthogonality relations? So if, let's say n in this case was 4, this would be the square root of 5. This would be 4 psi 4 star psi 5 dx. Well, by this rule, m would be 4 and n would be 5. Those are different, and this integral is 0. Look over here. If n was 4 again, this would be square root of 4, and this would be psi 4 star psi 3 dx. Again, by these rules, m is 4, n is 3, and this integral is 0. And so the entire answer for the expectation value of p for the nth state in the harmonic oscillator is 0. Okay, so you are going to have a worksheet in which you're going to calculate a couple of these expectation values. Okay, actually just one for now, and then in the test you'll have a couple more. All right, we'll see you next time. Let me see if I can turn this off, and I'll upload your worksheet.